Welcome to this comprehensive guide on C-sharp async and await patterns. These are essential for building responsive applications, especially in game development for smooth user experience and in API interactions where network delays are common. Mastering them enhances your ability to create fluid, non-blocking user interfaces. Asynchronous programming allows tasks to run without blocking the main thread, which is crucial for maintaining application responsiveness. It enables operations to execute in the background, freeing the main thread for UI updates and user input. This ensures a fluid and interactive user experience during intensive tasks. Imagine a game freezing every time you load a new level or fetch data. This jarring unresponsiveness is the direct problem of blocking the main thread. It creates a frustrating user experience, making the application feel slow and unreliable, severely impacting player enjoyment. In GUI applications like games, the main thread handles all user interface updates and processes user input. Blocking this vital thread prevents these duties, leading to a frozen UI and ignored input. This inevitably results in a severely degraded and poor user experience for the end user. C#S async and await keywords provide an elegant solution to blocking the main thread. They enable non-blocking operations, allowing your application to initiate long-running tasks and gracefully pause execution. This paradigm ensures your application remains responsive and interactive, preventing frustrating freezes. The async keyword marks a method as asynchronous, allowing it to contain await expressions. It signals the method can perform work asynchronously. This keyword enables the compiler to generate the necessary state machine for asynchronous execution, but doesn't inherently run the method on a separate thread. The await keyword pauses an async method until the awaited task completes. Crucially, this happens without blocking the calling thread, freeing it for other work like UI updates. Once the task finishes, the async method seamlessly resumes, maintaining responsiveness and making the process appear synchronous. Let's look at a practical example: making non-blocking API calls to fetch data from a server. Retrieving data often introduces network latency. Asynchronous API calls are vital to ensure your application remains fluid and responsive throughout these data retrieval operations, preventing frustrating UI freezes. Traditionally, an API call would halt your application until data arrived, causing a noticeable delay. The application would stop and wait, doing nothing else, until the server responded. This forced waiting period creates a frustrating delay, making the application appear frozen and unresponsive to the user. With async and await, the application remains responsive while waiting for the API response. The application initiates the request and immediately returns control to the calling thread. This means the UI remains fully interactive, allowing users to continue interacting while data is fetched in the background. Data then seamlessly populates the UI. Here's how you might structure an asynchronous API call in C#. Define an async method, often returning task T. Use HTTP client for the web request and await methods like getAsync. Crucially, include try-catch blocks for error handling to manage network issues gracefully, ensuring a resilient application. Another common use case is managing long-running game logic or complex calculations without freezing the game. Imagine AI pathfinding or procedural content generation. Executing these synchronously would cause the game to stutter, lag, or completely freeze, destroying player immersion and enjoyment. For CPU-bound tasks, operations primarily consuming processor time, task.run is invaluable. It offloads intensive work to a separate thread from the .NET thread pool. This allows the main thread to remain free and responsive, ensuring heavy computations proceed in the background without impacting interactivity. This allows the main game loop to continue rendering frames and processing input while heavy computations happen in the background. The game remains perfectly smooth and responsive, even during complex AI decisions. Players experience no lag or dropped frames, significantly enhancing their overall satisfaction. Consider loading large game assets like high-resolution textures or 3D models. Doing this synchronously forces the game engine to pause until every asset is loaded. This inevitably causes significant hitches or freezes, where the screen momentarily locks up, leading to a jarring and frustrating player experience. Asynchronously loading files ensures a smooth transition and a better player experience. Instead of freezing, the game can display a continuous loading screen with animations while assets load in the background. This non-blocking approach means the player perceives a continuous flow without abrupt pauses, leading to a more polished game feel. Here's a code snippet demonstrating how to load a file asynchronously using task.run. Within an async method, you would await task, run, and then execute the file reading operation, such as file.readAllTextAsync. This pattern moves file I/O off the main thread, keeping your application responsive. Now, let's dive into essential best practices for using async and await effectively. Adhering to these guidelines helps prevent common pitfalls, improves code readability, and ensures the robustness and maintainability of your asynchronous C# applications. These practices are key to harnessing their full power. First, embrace async all the way. If a method calls an async method, it should generally also be async and await the result. This creates a consistent asynchronous call chain, ensuring non-blocking behavior propagates upwards. Breaking this chain can lead to deadlocks or unexpected blocking. This prevents blocking higher up the call stack and maintains the asynchronous flow. If an async method is called synchronously, it can still block the calling thread, negating asynchronous benefits. Maintaining this unbroken flow ensures responsiveness is preserved from lowest level operations to the UI, providing a seamless experience. Next, follow appropriate naming conventions. Asynchronous methods should typically end with the async suffix, for example, getDataAsync. This provides immediate clarity, signaling the method is asynchronous and should be awaited. It prevents accidental synchronous calls and improves code maintainability and understanding. This clearly indicates to other developers that the method is asynchronous and should be awaited. This visual cue communicates that the method returns a task or task T. Without this convention, distinguishing between synchronous and asynchronous methods is harder, potentially leading to incorrect usage and difficult to debug issues. Proper exception handling is vital. Use try-catch blocks around await calls to gracefully manage errors. Exceptions from an async method are wrapped in the return task and rethrown when awaited. This makes try-catch the appropriate mechanism for handling them, ensuring your application remains stable. Unhandled exceptions in async methods can lead to application crashes or unexpected behavior. If not caught, they propagate up the call stack, causing immediate application termination or leaving it in an inconsistent state. This results in a poor user experience and makes debugging incredibly challenging without proper error logging. Avoid async void for most scenarios, especially in library code. Prefer async task or async task T for methods that return a value. Async void is primarily for top-level event handlers where await completion is not possible. Its use outside this context can introduce significant challenges and unexpected behavior. Async void methods make exception handling difficult and can lead to unexpected application termination. Exceptions from async void methods cannot be caught by a try-catch block in the calling method. Instead, they are rethrown directly on the synchronization context, often causing the application to crash without clear error indication. In library code, consider using configure await when awaiting tasks. This instructs the runtime not to capture the current synchronization context when resuming after await completes. This allows the continuation to run on any available thread pool thread rather than being forced back onto the original context, which is important in UI applications. This prevents deadlocks by telling the runtime not to capture the current synchronization context. You avoid scenarios where an async method's continuation tries to resume on a UI thread that is already blocked. This significantly improves performance through flexible thread scheduling and the overall reliability of your library code, ensuring predictable behavior. For concurrent tasks, use task.whenAll to await multiple tasks simultaneously. This method allows you to initiate all tasks concurrently and then wait for the last one to finish. It returns a single task that completes when all provided tasks have completed, making it incredibly efficient for parallelizing operations. This is more efficient than awaiting each task individually, especially when their order of completion doesn't matter. Awaiting tasks one by one means subsequent tasks only begin after the previous one completes. Task.whenAll allows all tasks to run in parallel, maximizing resource utilization and dramatically reducing overall completion time. Finally, implement cancellation support using cancellation token for long-running operations. This mechanism provides a cooperative way for an external entity to signal that an ongoing operation should be stopped. Without cancellation, a long-running task might continue consuming resources unnecessarily, leading to wasted processing power. This allows users to stop tasks that are no longer needed, preventing resource waste and improving responsiveness. Users can gracefully cancel operations like file downloads or report generation. This frees up system resources and significantly improves the application's perceived responsiveness, adapting quickly to changing user needs. Now, let's summarize the key benefits of adopting async and await. Understanding these advantages will reinforce why these powerful asynchronous programming patterns are indispensable tools for modern application development. They are crucial for performance-critical domains like game development and API interactions. Improved responsiveness is a primary benefit, ensuring your application remains interactive even during heavy workloads. By offloading long-running operations, your UI stays fluid. Users can continue to interact even during heavy computations or network responses, leading to a smoother and more professional feel. This directly leads to a better user experience, as users appreciate applications that don't freeze or lag. By preventing unresponsiveness, async and await contribute to higher user satisfaction and a positive perception. A smooth, uninterrupted experience is a hallmark of high-quality software. Increased efficiency is another advantage, as resources are utilized more effectively by not blocking threads. When threads are blocked, they consume resources without useful work. Asynchronous programming frees up threads to handle other tasks while an operation is pending, leading to better overall performance and scalability. Finally, async and await simplify asynchronous code, making it easier to read and maintain compared to older callback-based approaches. They allow you to write asynchronous code that reads almost synchronously. This significantly improves code readability, reduces bugs, and makes your codebase easier to understand, debug, and extend. In conclusion, C# async and await are indispensable tools for writing modern, high-performance, and user-friendly applications. These patterns provide a robust and elegant solution to the challenges of responsiveness and efficiency. Mastering them is a critical step in becoming a proficient C# developer in today's demanding software landscape. By understanding and applying these patterns, you can create responsive games that never freeze or stutter, even during intense loading. Furthermore, you can build highly efficient API integrations that fetch data seamlessly without blocking the user interface. These skills are paramount for delivering top-tier performance and user satisfaction. Mastering asynchronous programming with C# async and await will significantly enhance your C# development skills. It opens up new possibilities for designing more robust, scalable, and performant applications, making you a more versatile and valuable developer. Continue to practice and explore these concepts, as they are foundational. Thank you for watching this tutorial. We hope you found the explanations, examples, and best practices helpful, empowering you to build more responsive and efficient applications in your C# projects. Don't hesitate to revisit this guide, and remember that practice is key to mastery. Happy coding!